Hello, friends. Welcome to the part 2 of the inventory optimization. In part 1, we have covered about the mandatory or the important master data that are required for IO to run successfully. Also, we have covered the basic input key figures like IO cells and forecast, which are required as a part of the input. And we have also talked about the primary output, that is the recommend safety stock or the recommend safety stock in days, that is generated as an output of the inventory optimization. Now, inventory optimization considers multiple inputs. Some are in terms of master data, some are in terms of variability. The inputs that are considered as a part of the master data, the most important of those master data are something that we have covered in our previous examples or in the previous video. Now in today's video, we are going to cover the second set and the most important set of inputs based on which IO determines what should be the right mix of recommended stock at a product location combination in a full network. Inventory optimization primarily takes three variations into account. The first and foremost is called demand variation, or which is also known as the forecast error CV. The second variability that it considered is lead time variation or lead time CV or covariance. And the third that it considers is production lead time variance or the production lead time covariance. Out of all these three, the most commonly used is the demand variability, because demand variability gives us how accurate was our forecast at a past date based on the sales history that we have got. Now, this is one of the primary input for IO. Now, in a normal standard scenario, as we have talked about, IO cells is the key figure that stores the history in the past, and IO forecast is the key figure that holds forecast in the past that has been generated as well as forecast in the future. Now, in most implementations, the requirement comes in such a way that business doesn't want to do the forecast error calculation or the forecast covariance at a product location customer group level. And there could be multiple reasons for that. One such important reason is the demand planning for those customers happen altogether at a different level. They do demand planning at a much more aggregated level and then disaggregate the forecast into product customer or product location customer or product location per se. So ideally, in order to maintain a consistency, the covariance of the forecast error should be in line with demand planning. And for example, let's say we are generating forecast and forecast error in demand planning at a product group or a product brand level. So the covariance that we will run for inventory optimization ideally should follow the same level so as to maintain a model specific consistency. So here the screen that you are seeing here is the forecast error calculation profiles. So if you look into the planning area on which I am working on, here if you see I have created two profiles. One is to run forecast error at month prod lock level, and the other is to run forecast error CV at a business unit class and style level. One thing very important to remember is, in order to run forecast error at a aggregated level or a level that is not standard, we need to make sure that the key figure that we are using for the forecast error calculations input and the output key figure should be on a same planning level, and if that planning level is custom in nature, it is very important for us to create custom master data to represent that level. So just to take an example of this forecast error calculation that I am running at a BU class and style level, I could have easily created a planning level including this BU class and style as a root, select that planning level in a calculated key figure and run that forecast error CV. But that doesn't work. You need to have your key figure stored, and those stored key figures should be at the planning level on which we want to maintain our forecast error CV. And that leads me to the fourth master data, the custom master data, which I showed you before. And in this custom master data, what I am doing is using the help of CIDS. I am creating a combination of product class, product owner, and style, so that with the help of this custom master data, I create a planning level wherein these three are the roots and the key figures that are used for inputs in the forecast error calculation, and the key figure that will be used as the output for this forecast error calculation all reside in the same planning level that refers to this master data. Now I will take you inside this forecast error profile. Now if you see at the header level of this profile, just bear with me a few minutes because this takes some time to load. I don't know why, but it takes time. So if you see, this profile description is running at a month, product owner, product class and style level, and this is the planning level of the key figure, or this is the planning level at which the forecast error is supposed to run. So similar to key figures like IO sales, IO forecast and IO forecast error CV, I have created additional custom key figure at this level, wherein I am copying the data of the IO cells and the IO forecast to these respective key figures, that is actuals net booking at BU class, unconstrained forecast quantity at BU class, and I am also using IO forecast error CV at BU class, so that the input key figures and the output key figures are at the same level. So it is very important whenever you get a requirement of calculating covariance which is not at a standard level, you need to make sure that you create a custom master data of the level on which you want to do the forecast error calculation, and the input output key figures for the forecast error calculation should reside at the desired planning level. So here I have used forecast error. Function is forecast error at lead time. These are the sales entries, actual sales at BU style input. This is the forecast at BU style. I am using the covariance method, and the output I am storing it at a key figure called forecast error CVBU class and style. So the planning level that we have defined in the header, I can select historical sales key figure and forecast key figure, and those key figure needs to be present in the planning level that I have defined in the header. So that is the reason I have used these two key figures. And what I have done before that is, so if you see I have IO forecast, similarly I have IO cells. I have used a copy operator to copy the value of IO forecast and cells to this respective key figure, so that at this level I have the history and the forecast, and based on this history and forecast I am in a position to run and generate the output of the forecast error at the same level. Here if you see, the horizon that I have taken is this calculation happens in the past. So I have taken 1 month with an offset of 0. That means generally in the current month you don't get proper sales history updated. So that is why the month before the current month is the starting month, and I am going back 4 months to check the history and the forecast, and based on this horizon I am generating the forecast error CV at a BU class style level, and the planning level is product owner class style and product style level. One thing if you remember, at the header level the planning level was at a month. Here it is without a month, and there is a reason for that. Because forecast error, based on the historical horizon, whatever forecast error is generated, the forecast error gets generated at a current bucket level. So in this case, it is not necessary for me to have a planning level with a time period. I can have it without a time period, and then I can extend it or extrapolate it to other time period using different options. So here I am using the covariance, and the calculation method I have used is mean absolute percentage error, MAPE. Apart from that, there are few other settings that I have done, which I am saying if the forecast error is 80 or more, that means you don't have to put anything above 80. Anything more than 80 you make it 80, because a forecast error of 80% is already very pathetic, which says that I don't have correlated sales and forecast in the past so as to generate a good error CV. So 80% is already quite bad. So anything above 80 is also bad. Apart from that, I have also used number of period for which the sales and the forecast needs to be considered, along with sales forecast, intermittency, and how much period is required. You can take a look. There is a big documentation for that mentioning what is what. So based on this, I have created a forecast error profile. So once this is done, Here, if you see at this level, which is the product owner class and style level, I have copied the IO forecast to a key figure called demand BU style, and similarly I have copied the key figure IO cells to a key figure called demand BU sales history. And based on that, I have got the error CV generated at this level. So if you see, I have got a variety of error CV, which starts from having good forecast error CV to a pathetic forecast CV of zero point 0.8, which at this level denotes that at this custom planning level I have successfully executed my forecast error CV. Now once that is done, one thing to remember is IO doesn't recognize this forecast error CV. So as a next step, my objective is to copy this forecast error CV generated at a BU style level to its actual level, which is product location and customer. And for that I have used a copy operator wherein I am copying this same value to all the products that belong to this combination. So if you see in this style, class and residential, I have got a forecast error of zero point 0.5. So if I go and look into the products that belong to this style ID, you will see all these products that belong to the style ID 21000 has all got the same forecast error CV of 0.45 populated. And similarly, as discussed before, based on the ABC segmentation, I have also populated the demand stream that is needed as a part of the IO. So at this point of time, what we have done is we have generated the forecast error at an aggregated level, copied the generated forecast error CV to the product location level, which is understood by the IO. Now comes the next part of the covariance, which are not as much used as the forecast error covariance. The next most commonly used is lead time covariance. For lead time covariance, there is a complicated logic which we built, but as of 2004, IBP has introduced a functionality called lead time variability, through which we can introduce certain key figure from where it will extract the historical transportation lead time using the standard extractor, and based on that it will generate the lead time error CV as well as the production error CV, and we can use those error CV into the respective location source and production source of supply. So before I go there, I will give you a glimpse of how it works. This is a lead time, this is a new app that is called Supply Lead Time Profiles. If you see here, I have created IO lead time CV. Inside this, we have to give certain inputs in order to calculate the error CV. First and foremost, the calculation level at which I am doing it is at cal week prod lock from, because this is the one that I am generating for location source lead time. If I would want to generate the supply lead time at a production level, I would have used cal week prod lock source ID. But in this case, since I am calculating the error CV for lead time, I have used this planning level. The calculation horizon I have selected as 52 weeks with a minimum number of period as 12. The default lead time as I have selected zero point 0.2 and the maximum lead time covariance is zero point 0.5 with a confidence level of 95. I am not using any outlier handling method to calculate outliers within the lead time because that will be overkill at this point. And based on this, these are the input key figure which is basically time series historical lead time, and based on this lead time the system generates the average lead time, the average lead time standard deviation, the lead time covariance, the lead time upper limit and the lower limit. So these are required for other purpose, but for the purpose of IO I am only interested in this lead time error CV. Once we get this data populated in this key figure and run it, the lead time error CV will be populated here, and using a copy operator I can copy this value from this key figure to the lead time covariance key figure. Due to lack of data, everything has been generated as zero point 0.2, and you can see that the transportation lead time covariance has been generated as zero point 0.2 against all the lead time between a source and destination and a product and a particular product. Similar to this, we can create one more lead time. In this case, that lead time will be not for location source but from production source header in order to ascertain the production source lead time. For that I can create one more lead time. The only difference is here I will select calweek prodlock src and I can give the horizon as I want, and the input key figure here will be different. It will be T hist P lead time denoting the P lead time, and based on that it will generate the lead time covariance in T hist P lead time CV, which is the covariance of the lead time CV. Since I have done that before, in this case if you come and look into the production source header, you will see that for the production source header against the lead time, the 0.02 has been updated. Because since there is no data that is coming from the source system, hence the default value is being picked up. So this is how the three primary lead times, that is the demand variability, the lead time variability and the production lead time variability, these three variabilities can be generated, and these three are then used as an input in IO in order to determine the right safety stock at a product location combination at a weekly or at a monthly level. So this completes the part 2 of the session, wherein I have showed you what are the lead times that are involved. With most commonly used lead time is the demand covariance or the demand lead time. Then the next most used is the supply variability in order to determine the delays in my supply chain, most from a vendor side. And the third one, which is very less used, and that too in complex production scenarios where I have multiple source IDs to determine what is the production source lead time for a particular source ID at a product at a location. So this Part 2 and Part 1 covers primarily the required inputs that are needed for the inventory optimization to take into consideration and give a feasible recommended safety stock or feasible recommended days of supply, which we can then further utilize and pass it on to supply so that the safety stock recommendation is accepted by the system. Now, this is what I wanted to cover in this session or part 2. In part 3, I will cover how to configure the inventory optimization profile and how, by taking all this input, how the system is generating the inventory optimization or the recommended safety stock, and how we can leverage it and use it as an input in supply planning. That's all I wanted to cover. Thanks a lot. Thanks a lot for your time, and I appreciate the presence that you spend on looking into this video. And if you like this video, please don't hesitate to subscribe and click on the bell icon, my friend. Thank you.